subscribe.
Hey y'all, welcome back. Today we are reviewing, which is all about limits, with a little bit of piecewise functions mixed in there. Let's take a look at number one. We've got this piecewise function that's graphed over here. The dark dots are going to be where the function's defined, and I'm not sure why these aren't white. They turned out gray, but those are going to be places where it's undefined. So we're going to use this graph to answer all these limit questions. Before I do any of the limit questions, let me go over, I kind of wish these function questions came first here at the end, so I'm going to do those first. So here we're just evaluating the function at this x value. So for example, g of 1, if I go to my x is 1, make sure you're not reporting back the open circle, that you're reporting back the closed circle. So g of 1 here would be 3. G of negative 1, again, make sure you're not reporting back 2, it should be 4. G of 6 is going to be 3. And so I think this is just trying to get you to make sure that you are seeing how to evaluate these functions when you have one dot that's closed and one that's open. Okay, so now let's start talking about limits. So we'll just start here at the beginning, the limit as x approaches 3. Now to make sure that any of these limits exist, we do have to check the left and the right hand limits to make sure that they are equal. So, let's take a look at x equals 3. This one's defined for x equals 3. It's actually continuous at that point. There's no break or anything. The left hand limit does equal the right hand limit, so it's just going to be 0. At x is 1, now here the function is not defined here, but that's okay. A function does not need to be defined in order to have a limit there. You just have to make sure that the left and the right hand limits agree. So in this case, the left hand limit, as we follow this graph, as x approaches 1 from the left, the y value is approaching 2, and we see that to be the case on the right hand side. So in other words, if you follow this up from the left and you follow the graph from the right, both of these are sort of pointing in the same direction to this point, which is going to be the value of the limit here, which is 2. Now when you see a minus or a plus sign in the top right corner, kind of like where you would see an exponent, like this next one has 6 minus, what this means is the left-hand limit. Okay, so I'm going to make a note here just for the sake of being clear. So you're going to approach 6 from the left. Okay, this is a left-hand limit. Maybe I'll just say that. Maybe that'll be a little bit more efficient way of saying it. So we're saying it's a left-hand limit. If you see a little plus sign there, so here's another minus, so this would be another left-hand limit. Actually, none of these have plus. Let me see if I can, okay, so down here we see we've got a plus. This is what it would look like if you had a right-hand limit. So for the left-hand limit, we don't need to check to see that both the left and the right-hand limits are the same. We only need to check it from the left. So we're going to go to where x is 6, and if we approach 6 from the left, so if we follow the graph to the left, we can see that we're getting closer and closer to 3. Now, if we find the limit as x approaches 6 from the right, if we follow the graph this way, now the arrow is pointing towards y equals 5. So the right-hand limit here would be 5. It's not asking for that, but just so you can see the difference. And since these two limits are not the same, right? The left-hand limit's 3, the right-hand limit is 5. We would say that the limit as x approaches 6, as a whole, would not exist. We'd say DNE does not exist. The limit as x approaches negative 1 from the left, so let's go to negative 1 here. And we already know that negative 1, not positive 1. So as we approach negative 1 from the left, we're getting closer to 4. If we were approaching it from the right, the answer would be 2 for the right-hand limit. Since these two limits are not the same, we would not be able to give a value for the limit as x approaches negative 1, but we can give a value if we just give one of the one-sided limits here. So as x approaches negative 1 from the left, the value of the function is approaching 4. The limit as x approaches negative 1, we just kind of talked about that. So since these left and right-hand limits are not the same, right? The left-hand limit equals 4, but the right-hand limit would equal 2. We say does not exist. There is no limit there. as x approaches 0, well, we are continuous at 0. The value of the function is just 0, and the limit on either side is 0, so this whole thing will just equal 0. All right, let's go to number 2. For number 2, we've got a piecewise function. Let's go ahead and sketch a graph. It does ask us to do that, but I think even if it didn't, it would be worth sketching out the graph just to kind of get a better feel for what's happening with the function. So it says that the first piece is y equals negative x. So that's just going to be a line that has a y-intercept of 0 and a slope of negative 1. So it should basically make like this 45-degree angle measure. All right, so something like this. Okay, now this piece I only want to be defined for when x is less than or equal to 0. So I actually don't want this right-hand portion of it. I just want it to go up to 0, and that's it. And I'm going to plot a point right here. I'm going to do a close dot here because it does say less than or equal to. For the
square root of x
basically does something like this. We can start to answer these limit questions. And so really what they're trying to get you to understand is what the limit as x approaches 0 is. So as I approach 0 from the left, so it's like I'm approaching x equals 0 this way, the value of the function is going down to 0. It's getting closer and closer to 0, which is what the value of the function at 0 is. Okay, so the limit from the left, and it's actually the same as the limit from the right. They're asking for the right-hand limit first. But you can see from either side we are approaching 0, so that means the limit does exist and it's going to be 0. So actually, the answer to all these questions is just 0. This is the right-hand limit is 0, the left-hand limit is 0, and since these two are the same, that is what the overall limit is going to equal. For number 3, we're trying to find the value of k that makes this limit exist. So on the first day, when we answered this question, it was worded a little differently. The way that I worded it was find the value of k to make the function continuous. And that is kind of what we need here. We need it to be continuous, or that would be like the easiest way, I think, to make sure that this exists. So let's go ahead and follow the same steps that we did. And if you want a little bit more explanation here, go back to the 12.1 notes, or the first lesson on this unit. Not 12.1. Oh, yeah, 12.1 notes, I think it was. But whatever the first lesson was of the unit. And I go into a little bit more detail on how to solve a problem like this. So essentially what we need to do is we need to set the two pieces equal to each other. So the square root of x plus 7 equals x squared minus x plus k. And we want these to be the same. We want these to be equal where x is equal to 2, because 2 is where that switch over is happening, where we're switching over from the first expression to the second. So what I'm going to do is substitute in 2 for x, and then we're going to solve for k. All right, so 2 plus 7 is 9, and the square root of 9 is going to be 3. 2 squared is 4, and 4 minus 2 is 2. So we get 3 equals 2 plus k. So I think it should be pretty obvious what k is going to be, but algebraically, what you would do is subtract 2 from both sides, and you'd get 1 is k. So that about wraps it up for page 1. Let's go on to page 2. Number 4 says we've got this piecewise function and is wondering whether or not the limit as x approaches negative 2 exists. Let's take a look at the graph, see what would this actually look like if we graphed it. And in order for that limit to exist, we need the left and the right-hand limits to agree. So as long as the function equals the same thing, since both of these are continuous, if they both equal the same value at x equals 2, then we can determine that the limit exists because, like I said, both of these in and of themselves are continuous. So we've got the first one's 2x plus 10. So like if we're up here at 10, the graph's going to be going down with a slope of 2. So let's see if I can make this look halfway decent. Yeah, it's going to be about close enough. And so this would be -5 right here. And then the next one would be -x plus 4. So -x is going to do something like this. And the split's happening at -2. So as long as -2 is right here, we are good. And so because the first one is only going to be good for when x is less than or equal to -2. So it's going to be like just this piece right here and not this right-hand piece. And then for the second one, it says x is greater than -2. So as long as my rough sketch here is halfway decent, as long as these two pieces are connected, then we can say, yeah, this limit does exist. Like I said, this is a rough sketch. This is not really a great justification. I'm not even using a grid here. This is not to scale or anything. Just a quick sketch. So really to justify my answer here, what I need to do is I need to plug in -2 into both of these. So -2 times 2 is going to be -4 plus 10 equals 6, which is kind of where I'm expecting this intersection to happen if it does. And then -2 be +2 plus 4 is also 6. So yeah, these both equal 6. That means this intersection is occurring at 6. Maybe I'll just write 10 here a little bit clearer so you can really see what I'm saying here. Okay, so since both of these are the same, then yes, the limit does exist. We can say yes. Yes, the limit exists because the function is continuous. Okay, it's actually continuous for all real numbers. So that's enough to say, yeah, any of the limits, the limit as x approaches anything will be defined as long as, we're not talking about infinity here. Okay, so number 5, what are the 3 conditions for continuity of a function at a point? So this is just kind of a definition question. What's the best way I can show this? We'll say the limit, the left-hand limit has to be defined and has to equal the right-hand limit. The function has to be defined and the function has to equal the limit. So we want to say that the limit as x, okay, I might have to do this in chunks here. The limit as x approaches c, so c is just any point, of f of x has got to equal some value, okay, so or we could just say is defined. We also need to know that the function is defined at that point, okay, so we'll say that just f of, so this is going to be the second bullet point. Here's the first bullet point, okay, so here's condition 1, condition 2, condition 3. So condition 2 would be that the function is actually defined at that point. So f of c, like if I plug in whatever this number is, that needs to be defined as well. And then the third one is that these two things are equal. So in other words, that the limit as x approaches c actually equals f of c. And so those are going to be the 3 conditions for continuity. For number 6, it says, what are the 3 most common types of discontinuity? So the most common types that we've had to deal with, the first one is a hole. Okay, that's called a removable discontinuity. Discontinuity. Okay, trying to spell there. Okay, the second one is a jump. So like we've seen the jump function, or if you have a piecewise function where the 2 pieces don't actually touch each other, this is a non-removable discontinuity. Number 3 is going to be a vertical asymptote. And that is another example of a non-removable discontinuity. Now there are other types of discontinuity, but these are going to be the most common ones, and you're not going to see really anything else besides these three, for this course at least. For number 7, it says find and classify all the points of discontinuity. Okay, so we can see that there's one at 3, one at 1, one at 2, and that looks like it's it. So we'll just go one at a time. So I'll say at x equals -3, there is a hole, which is again, a removable discontinuity. Okay, the next one is going to happen at x equals 1. Okay, this is going to be another hole. All right, the left and the right-hand limits do equal each other. So since this limit exists, then we have a removable discontinuity. And then the last one is going to be at x equals 2. That's going to be a jump, and that is a non-removable discontinuity. So no vertical asymptotes on this one. Did I miss any? No, just 1, 2, 3. Yeah, that's it. Okay, so those are going to be all the different points of discontinuity. All right, let's move on to page 3 here. For number 8, it's asking whether or not this function is continuous at x equals 5. Okay, now if we just look at the rational function above, or the rational expression part of this function, that numerator is a difference of 2 squares, so we can factor it as x plus 5 and x minus 5. And so you might notice that both the numerator and the denominator here have a factor of x minus 5, right? So x minus 5 over x minus 5. And so that means there's a hole in the graph, okay? But this is kind of giving you an out here, saying, okay, well, we're only going to let this define the function when x isn't 5, but if it is 5, it should equal 10. And so the question is it actually continuous at x equals 5? Well, that all depends on whether or not this 10 is actually filling that hole. So we need to go back and find the hole equation here, which is what we get when we cancel out these two x minus 5s. Okay, so I'm going to just make a note here. So this whole equation, which is going to be have all the same values, except the hole will be filled in. And if that hole is filled in such a way that 5 comma 10 is a solution, then yeah, it's continuous. Basically, this is going to be a point at this x value, and if 10 is where the hole is, then we're good. Then it's continuous. So the whole, sorry about that. The whole equation is going to be just x plus 5, right? Y equals x plus 5. That's what you get when you reduce the x minus 5s to 1. And so if I plug in 5 here, then y is going to equal 10. 5 plus 5 is 10. So since that value is the same as how it's defined in the piecewise function, then basically what this is saying is, hey, we're just plugging in the hole here. So, so this would be continuous. Yes, this function is continuous. Actually, it'll be continuous everywhere, but specifically at x equals 5, although there are no other points of discontinuity, because the point 5 comma 10 is defined. Okay, so that's right here. Number 9, we've got another one of these limit problems. We had, one of these like at the very beginning. Okay, so same kind of questions here. Does the limit as x approaches 2 exist? Well, yes, because you can see that the left-hand limit equals the right-hand limit. It doesn't matter that the function, that the value of the function is not equal to the limit. The limit does exist, and in this case, it equals 2. Oh, so this is just true false. It's not actually asking what it is. Oh, so this will be even easier. So yeah, this is true. Does the limit when x approaches 3 exist? Yeah, in fact, it's continuous there. There's really no problems there. There's no point of discontinuity or anything like that. The limit as x approaches 4. Now, that one does not exist, okay, because the left-hand limit here is going a little bit below 2. The right-hand limit is going towards 4. We have a jump here, a non-removable discontinuity. So, yeah, this is going to be false. The limit as x approaches 5 is going to exist. Yep, absolutely. It's continuous on that right there, so no problem computing the limit. The function f is continuous at x equals 3. Yeah, it is continuous at x equals 3. The left and the right-hand limit agree, and the value of the function equals that limit. So, yeah, this is going to be true. All right, so number 10 is asking you to look at the graph and a bunch of more true false questions. Okay, so and there's quite a few here, so that's all right. All right, so it says the limit as x approaches 2 from the left is equal to f of 2. So let's see if that's actually true. So as I approach x equals 2 from the left, I'm approaching -1. So the value of this is -1, and then the value of f of 2 is also -1. So these two things are equal, so we're going to say true. Okay, the limit as x approaches 6 from the left is -1. Okay, so we're pointing towards -1. And the limit as x approaches 6 from the right is -1 as well. So yeah, this one will be true. Another true statement here. Now, does the limit, now since both of these, since the left-hand limit and the right-hand limit are the same, then the limit as x approaches 6 is -1. It should be equal to the same thing. Now, the value of the function, f, if we plug in 6, it's actually not -1 here. It's actually -3. So these two things are not equal, so this would be a false equality. Is the function continuous at x equals 4? Yes, absolutely. The left-hand limit and the right-hand limit are the same, and they're equal to the value of the function there. So that is going to be true. However, f of x is not continuous at x equals 2. The left-hand limit and the right-hand limit do not agree. So right away, we can say that it's not continuous. We don't even have to check what the value of the function is there. The range of the function is from -3 to 2. That's going to be false because there are no values between -3 and -1. Okay, it is defined for -3, so that would be in the range, but you'll see there's no part of the graph going on between -1 and -3. There's no graph here, right? Oh, I went a little high there. Right, there's nothing going on in here. So these values between -1 and -3 cannot be part of the range. And so to say that the range includes those would be false. Number 11, what values of k make the function continuous? All right, so this is going to be solved kind of like how we did, which number was that? I guess it was a little while ago. Let's see. Number 4 is kind of a similar question, right? No, it wasn't number 4. I'm sorry, it was number 3. So yeah, go back to number 3 if you want to see another example that's kind of like this. But we're going to use the same strategy here, which is we want to set both sides, both pieces of the piecewise function to be equal to each other. And then we want it to be continuous. So what we need is for at x equals 0 for these two to touch each other. So we are going to plug in 0 everywhere where we see x and solve for k here. So now we're just going to go ahead and simplify this expression. Most of this should simplify pretty easy. E to the 0 is 1, and 6 minus 1 is just 5. 0 squared is 0, so we can just sort of ignore that. Now cosine of 0 is 1, and you can use your unit circle to verify that. And so now to solve for k, I need to add 1 to both sides, which give me 6 equals 3k, and then divide both sides by 3, so I get k equals 2. So that would be the value of k that would make this function continuous. Now, if you've got three pieces and you've got to do a similar thing here where you want it to be continuous, we need the first piece to match up to the second piece, but we also need the second piece to match up to the third piece. So to solve this, we're actually going to need to set up two equations and solve it as a system of equations. The first equation we'll set the first piece equal to the second piece, x plus 1 equals ax plus b. And then for the second equation, I'm going to get that by setting the, this piece, the ax plus b, equal to the third piece. So we'll have ax plus b equals x minus 3. Now we want different x's here for the two different equations because we want the first and the second pieces. So the x plus 1 and the ax plus b to collide or to basically intersect each other at this x equals 1. Okay, so that means I'm going to plug in 1 into this equation. And when I do that, when I plug in 1 into x, I get 1 plus 1 is 2, and a times 1 is just a. So what I end up with is a plus b equals 2. Now for the second break in the graph, where we're switching from the second equation to the third, I'm going to substitute in x equals 10 here, because that's where the break is happening between these two. So I'm going to plug in 10 into both x's, and so that's going to give me a times 10 plus b equals 10 minus 3. And when I simplify that, I'm going to get 10a plus b equals 7. So these are my two equations. And so I'm going to set up a system of equations over here using these two. All right, so let's go ahead. I guess I'll continue working over it here. So my system is going to be a plus b equals 2, and 10a plus b equals 7. So to solve a system of equations, I'm going to use the method of substitution. So I'm going to rewrite this first equation, and it doesn't really matter if I substitute for a or for b first. I guess I'll solve for a. And so a is going to equal 2 minus b. This is going to be an expression that I'm going to substitute into this other equation. So basically I'm going to take this 2 minus b and substitute it into a here. Now I'm just going to solve for b, and I'll use that value to help me figure out what a is. So I need to distribute the 10. Come on, what's going on here? There we go. So that would be 20 minus 10b plus an extra b here equals 7. So negative 10b plus b would be negative 9b. Then I can subtract 20 on both sides. Oh, is this really going to be a fraction? Okay, all right. So if I subtract 20 on both sides, I get negative 9b equals negative 13. So b is going to be this awesome number. Yeah, geez, 13 over 9. So there's b, and if we want to get a, we already established that a is 2 minus b. Oops. Okay, and so what I'm doing here is I'm taking this b value and I'm going to substitute it right here. And so I get a is 2 minus 13/9. Now, if we're going to subtract these, I'm going to try to not use a calculator here. 2 would be 18/9. And 18 minus 13 is going to be 5. So we get 5/9. Okay. So those are going to be the two values that will sort of fix this piecewise function. And by fix it, I mean make it continuous. Make it so the first piece will match up with the second piece when x is 1, and the second piece matches the third piece when x is 10. Number 13 says find and classify any discontinuities. Well, if I factor that denominator, what I'm going to get, because that is a difference of two squares, is x plus 6 times x minus 6. So there are two different types of discontinuities occurring here. We have a vertical asymptote when x equals 6. So we have a vertical asymptote, which is a non-removable discontinuity. Gosh, I don't know why I struggle to spell this. Discontinuity. Okay. At x equals 6, because of this x minus 6 is causing that vertical asymptote. And notice how we've got the same factor in the numerator and the denominator here. And so if you think back to our rational functions unit, we said that that causes a hole in the graph, and a hole is described as a removable discontinuity because the left and the right-hand limits are the same. Like basically the limit exists there. So, and that happens at x equals negative 6, because that's the value that make these factors 0. Okay, number 14, sketch a graph of this particular jump function. So jump functions are going to equal 1 or negative 1 depending on what this number is right here. So since this is x minus 1, that means that this the undefined piece here is going to be when x is 1. So when x is 1, y is going to be undefined. But to the right of that, like if x is a positive number bigger than 1, will just reduce to 1. But if it's below 1, it'll be negative, so it'll be below the x-axis. So what we need here is we need an open circle right here at 1, 1, with a horizontal line going to the right. And then we have another open circle. Remember, it's actually not defined at negative 1, going the other way. Okay, there's only one discontinuity here, and it is a hole. So we've got this removable discontinuity. Oh, wait, no, it's not a hole. I'm sorry, this is a jump. Yeah, this is definitely not a hole because the left and right-hand limits aren't the same. So yeah, what we actually have is a non-removable discontinuity, and we're going to call that a jump discontinuity. And that happens at x equals 1. For number 15, we're just evaluating a bunch of limits here. So in this case, as x approaches 3, this denominator is going to get closer and closer to 0. This is not something that we really talked about, but you might see that we're going to have a vertical asymptote here. We can go ahead and omit this problem because this is not going to come up on your test. We're only going to have infinite limits. I think there's a couple questions here that we really didn't get to, so don't worry about this one. This other one we can probably answer even though we didn't see an example like this. This function y equals 6 is just a horizontal line. So the value of y is just always going to be 6, no matter what you're getting closer to. Now, if you want to answer this first one, I said you can omit it, and that's just because there's not going to be a problem like that on the test. But if you try to visualize what's going on here, we have a vertical asymptote at x equals 3. And if I plug in a value to the right of 3, because like the degree on the bottom is bigger, right? So our horizontal asymptote is going to be 0. If I plug in a value to the right of 3, like so let's say I plug in 5, I'm going to get a positive divided by a positive. So I know that my function has to be positive. And if I plug in a number that's smaller than 3, it's still going to be positive over positive because we're squaring here. I'm sorry, it'd be a negative over a positive. This will still be positive. Yeah, so positive should be positive. So if I plug in like a negative 5 or something, yeah, so actually, check this out. All right, oops, let me fix that up here. This is not going to look like that. Because if I plug in something like 1, I forgot about our x-intercept. We actually have an x-intercept at 0 here. So if I plug in something like 1, it's going to be a positive over positive, which would be positive. But since I do hit that x-axis and cross over, like if I plug in like a negative value, it will be negative. I'm still going to go towards this horizontal asymptote, But the point here is that as we approach 3, notice that on either side we're going up to infinity. So if we want to say the limit here, it's going to be infinity. But I do want to emphasize that there's not going to be a question like that on the test. Okay, so yeah, for this next one, since this function is just simply a horizontal line, y equals 6, you can say that the limit as x approaches just about anything. Well, actually, yeah, any real number here, any x value that's valid is always, it's just going to give you 6. Okay, so for this one right here, the limit as x approaches negative infinity. So as x approaches negative infinity, we're going to approach the horizontal asymptote. And since the denominator has the larger degree, it's going to be increasing the most quickly. And so when that happens, our our horizontal asymptote is y equals 0. So this limit's just going to be 0. And for this one, we've got, it's going to be kind of similar to this first one. This is going to be another one that you're probably not going to see one like this on the test, but it's still good to talk about limits and to review how these rational functions get sketched out. We have a vertical asymptote at x equals positive 3. And then we have an x-intercept of 0 and a horizontal asymptote at 1, because the degrees are the same here. So the ratio of the leading coefficients is just 1. If I plug in a number like 10, I'm going to get 10 over 7, which is greater than 1. So I've got this piece to the graph here. And then if I plug in something like 1, I'm going to get a negative. If I plug in something like negative 5, it's actually going to be positive, but we're just going to approach that asymptote. So the point here is that as we approach 3, the left-hand side is going to negative infinity, the right-hand side is going to positive infinity, and since those are not the same, we say it does not exist. All right, number 16. So all of these are going to be these infinite limits that we practiced, and so this is what we're going to need to do is compare both the numerator and the denominator to figure out where these limits are going. For number 16, we're finding a bunch of limits, and for the most part, what we want to be doing here is comparing the relative rates of change of the numerator and the denominator. So if you look back at what we talked about in the lecture, we saw that exponential functions grow more quickly than polynomial functions. So that means here the numerator is going to grow more quickly than the denominator. And for this, unless we had a negative sign out here, this is just going to go towards infinity. Now, this would be different if x went to negative infinity, because these exponential functions have a property where they're approaching 0 as x approaches negative infinity. So if that were the case, then you'd have like 0 over just anything, which would equal 0. So just keep that in mind when you have these exponential functions, that it really does matter if you're approaching positive or negative infinity. For this one over here, the logarithmic functions actually grow more slowly than the polynomials. So that means our denominator here is growing more quickly. And whenever the denominator grows more quickly, the function approaches 0. You've got a horizontal asymptote at 0. And we still have this plus 1, which doesn't change regardless of what x is. It's just always going to be plus 1. So this fraction is going to 0, this one right here. But the plus 1 is just, that doesn't change at all because there's no x to change. So we get 0 plus 1, which just equals 1. Exponential functions grow more quickly than polynomials, and they also grow more quickly than logarithms, which makes sense because polynomials grow more quickly than logarithms. So in this case, we have the numerator growing more quickly, and so we're going to say that the limit as x approaches infinity is just infinity. Again, if x approached negative infinity here, actually we'd have a bigger issue because that's outside the domain of natural log x, so I probably wouldn't even ask that. But just to make a quick note that e to the x would go to 0 if x goes to negative infinity. For the next one, we have pi to the x over e to the x. So when you have two exponential functions and you want to know whether or not the numerator or the denominator grows more quickly, you're going to compare the bases, and whichever base is bigger is going to grow more quickly. So make a little note here that pi is a little bit more than 3, and e is a little bit more than 2, so that means that pi must be bigger than e. Make a little note here, pi is bigger than Euler's number e. So since pi is bigger than e, that means the numerator is going to grow more quickly, and when that happens in a situation like this, the limit is going to be infinity. All right, for this one, we've got the limit as x approaches negative infinity. So again, we've got two exponentials here. We've got 3 to the x over 2 to the x. Now, as x approaches negative infinity, what we've discussed is that these exponentials go to 0. So as x approaches negative infinity, this is going to become closer and closer to 0, and this is going to become closer and closer to 0, which leaves us with just 0 plus 5 over 0. I'm sorry, 0 plus 4 over 0 plus 5. So that would just be 4 over 5. Okay, so for the next one, we've got 3 plus x squared over 2 plus x squared. In this case, no exponential, no logarithms, just a regular old rational expression with a polynomial on the numerator and the denominator, and they both have the same degree, right? They're both quadratic. So in a case where you have polynomials with the same degree, the horizontal asymptote is going to be equal to the ratio of the leading coefficients here, which is going to be 1 over 1. So since a rational function approaches the horizontal asymptote as x approaches infinity, then this is going to approach 1 over 1, which is just 1. The next one says that 4 e to the x, we have x approaching positive infinity, and the function is 4 e to the x over 2 minus 3 e to the x. So we do have two exponential functions here, and actually they have the same base, right? So this is going to be kind of a situation similar to the one we just did where the degrees were the same. Well, if they have the same base, then e to the x and e to the x are going to approach, they're going to grow at the same rate. So when we have one like this, we're going to have to compare the leading coefficients, kind of like we had to do in the last problem. So the leading coefficients here are going to be 4 over negative 3, which will just reduce, actually doesn't reduce at all, it's just going to be negative 4/3. So the next problem has a square root, and as I've been, I probably sound like a broken record here, but you want to rewrite this using a rational exponent. So we're going to rewrite square root of x as x to the 1/2, okay? So we have like the limit as x approaches infinity. Well, let me change that n. Yeah, there we go. Here, I'll just draw it out here. It might be easier. There we go. It looks a little more like what we've got over here. So anyway, we're going to compare the degrees here, and 1/2 is bigger than 2/5. So I'm going to make a little note here that 1/2 is bigger than 2/5. 1/2 is 0.5 and 2/5 is 0.4. So obviously the 0.5 is going to be bigger. Okay, so when the degree on the bottom is bigger, then this whole thing is going to get closer and closer to 0. So the limit as x approaches infinity is going to equal 0. Okay, only got a few more problems here left. For this next one, we just have a regular old rational function, nothing too funky going on here. We've got a degree 5 on top, degree 5 on the bottom. So as far as those are concerned, it's going to be growing at the same rate. So when that happens, we look at the leading coefficients, which is 2 over 3, and that can't be reduced or anything. So yeah, the limit is going to approach that horizontal asymptote, y equals 2/3, and so that is the value of the limit. If x is approaching negative infinity, okay, so here we're bigger on top, so this is not going to have a horizontal asymptote. So as x approaches positive infinity, the function is going to be going up, but as x approaches negative infinity, it's going to be going down. So as x approaches negative infinity, the limit is just going to be negative infinity. For this next one, we've got e to the x times e to the 15th. And as x approaches negative infinity, this exponential thing just becomes 0, or it's getting closer and closer to 0. So the closer this thing comes to 0, the closer we get to 0 times something. And regardless of what that is, if we're multiplying by 0, it's going to be 0. Not pi. So yeah, this thing just equals 0. Now, if this said x goes to positive infinity, then it would go to positive infinity. This thing would just grow without bound. But because we're going to negative infinity, this e to the x is going to 0. Our last problem here is just another good old-fashioned rational expression with the degree. You got a linear on top, a linear on the bottom. The degrees are the same, so we're going to examine the leading coefficients, which is 1 over 1. So this final limit is 1. And that'll be it for the review. So hopefully you kind of understand these limits a little bit better than when you started. Let me know if you have any questions, and please reach out and I'll try to help you out. But other than that, y'all have a great day.